Logarithmic functions are used to model and analyze all sorts of things in the real world that we might want to track. The magnitude scale is logarithmic and it uses a base of 10. That means if you add 1 to an earthquake's magnitude, you multiply the shaking by 10. Magnitude 3 shakes 10 times more as magnitude 2. A magnitude 7 quake shakes 10 times as hard as a magnitude 6 earthquake. So even if you don't end up being the person in a company who does the math and has to make these graphs and do the presentation, your comprehension of how things work in the world will be better informed if you have a big picture understanding of logarithms. And the probability that you're going to get graded on using logs in class is about 100%. At the end of this video, I'll link to a couple others to see how we're going to use logs to solve equations. They're easy to learn and work with even if you have no idea what you're doing. But in this video, I want you to get an understanding of what you are doing. We're going to talk about the backstory of logarithms pretty quickly. I'm doing that just so they won't feel so random when you see them in class. The word logarithm is strange, and the abbreviation log is just weirder. Log? Are we talking about trees? What's up with this? It's really uncomfortable. It's not something we worked with before. The word is the scariest thing about them, though, because the person who invented logs did all the heavy lifting for us.
Go. Good. Nice. Come on, Tammy.
Drive it up. Yeah. Come on, Tammy. Big push.
Lock it out. Yeah. Come on.
The year is 1594. No one knew how to solve an equation like 2 to the x power equals 8 without brute force. That one's not hard. I mean, x equals 3 because 2 times 2 times 2 equals 8. But what if you had to look at something else like 2 to the x power equals 1,073,741,824? Now, why would someone need to figure that out? Well, it could be a population. That just gives you an example of why these numbers could get really big and why we would be interested in knowing what those exponents are. That exponent's going to tell you the number of years it's going to take to get to that many people. These real life formulas that we're using to model things we see around us, they're not going to be linear straight line functions. They are going to be logarithmic functions, natural log functions, exponential functions. So back in 1594, a math guy in Scotland named John Napier started working on it with brute force. He started making tables of numbers. Now, in my imagination, I see this guy sitting down and he started with the 2's. 2 squared is 4. 2 cubed is 8, 2 to the 4th is 16. He probably organized it a little differently, but he just was going through this and multiplying these things out. And when he got done with the 2's, he moved on to the 3's. 3 squared is 9, 3 cubed is 27, and he did this for 20 years until he had 90 pages of tables. Now, the point wasn't to just make the pages. The point was to look for patterns and trying to figure out shortcuts for being able to solve when the unknown is an exponent. Eventually, he figured out what the shortcut was, and he named his invention logarithm. The first part, logos, is Greek for proportion or ratio, and the last part, arithmos, is Greek for number. So here we are working with logs, and they aren't wood. It's a tool that we use to solve equations. Let me show you a picture. Let's graph 10 to the x power, and let's graph log base 10 of x. And you can see these two visually are inverses of each other, but let's check a couple of points. So if I plot point A on the first graph, I get 0, 1. And on the second graph, A prime would be 1, 0. They just switch places. Another point, just to make sure it's not a fluke, B being 1, 5. On the other graph, B prime is 5, 1. And one more, just to make sure I'm making the point while I'm making points. Oh, yeah. C, 1, 9. C prime is 9, 1. These functions are inverses of each other. Inverse functions undo each other. Addition undoes subtraction, multiplication undoes division, and now we have exponents and logarithms as inverses of each other. Let's take the idea of why we're doing logs and put it in context with everything else you probably already know how to do. I can explain it all with a really simple statement here, which is 2 cubed equals 8. It has a base, it has an exponent, and it has an answer. 2 is the base, 3 is the exponent, 8 is the answer. So you could see a problem where you know the base, you know the exponent, you don't know the answer. Exponents are used for repeated multiplication. So in this case, you'll take 2 times 2 times 2 3 times, and you'll get the 8. This is easy, but if it's a more difficult problem, you'll use your calculator. If they don't tell you the exponent, but you know the base and you know the answer that you're trying to get to, what we really want to know is how many times is 2 multiplied by itself to get to 8. In order to figure this out, it's actually repeated division. This is why John Napier invented logs, to avoid having to do this with very large numbers. Watch me do this with the small numbers. We're going to take the 8, we're going to divide it by the base and get the 4. We're going to then take the 4 and divide it by the base again and get a 2. And then we'll take 2 and divide it by that base again, and when we get to the 1, we are finished. How many times did we do that? We did it 3 times. This is repeated division, which makes sense. If exponents are repeated multiplication and logarithm is the inverse operation for exponents, then logarithm must have to do with repeated division. Again, if this is easy, you'll just crank it out. If it's more difficult, you're going to follow the log properties for solving equations. That link in a minute, but you probably already saw this in class, or you're about to see this in class. What if you don't know the base, but you do know the exponent and you do know the answer? Well, you've probably already done these problems. This is when you're going to use roots. So in this case, the 3 is on the outside of your root because something cubed equals 8, so you've got to use a cube root. The answer is 8. That's going to go underneath the radical, and the base is going to end up being what we're solving for. And again, if this is easy, just do it in your head. If it's not, you're going to grab a calculator. All those log properties you're about to learn in class are going to help you solve equations when the variable is in the exponent. Now click into these videos right now to see how logs make short work of solving some very complicated equations. Thanks for watching. I'll see you next time. Bye.